Okay, so in order to really understand energy changes, whenever we're talking about alkenes, and specifically whenever we do reactions on alkene, we really have to understand basic concepts of thermodynamics and kinetics. So this isn't really math heavy, at least this take on it, but it's very important to make sure you understand the difference between thermodynamics and kinetics, because we're going to try to relate these reactions that we see by their energy. Let's imagine this theoretical reaction where we have this thing A, doesn't really matter what it is, and thing B. So for this chemical reaction, thing A is being converted into thing B. And what we're going to see is we can describe this reaction both by the thermodynamics that govern this reaction and the kinetics that govern the reaction as well. So whenever we're talking about thermodynamics, the question that thermodynamics is really trying to answer is how much of thing B is being formed. So this how much question has a tiny little caveat to it. So basically saying, given an infinite amount of time, how much of B is going to be formed at the end of infinity. And then the second thing that we can use to describe this reaction is the kinetics of the reaction. And so the kinetics are actually interested in something completely different, which is not how much, but how fast does the reaction go. And so in this case, kinetics is kind of like the polar opposite of thermodynamics, which is instead of worrying how much we form of B versus how much we form of A, kinetics really doesn't worry so much about that as much as it is just trying to describe whatever happens, how long is it going to take for that thing to happen. So before we can actually talk about thermodynamics and kinetics, we need to introduce this concept of a reaction diagram. And so if you take this reaction down below, what you are seeing is that we have this group or atom X bound to group or atom Y. So they're just random placeholders. It's kind of a generic reaction. So we have this bond between X and Y, and Z is just kind of sitting out here doing its thing by itself. If we put these two groups together and had them react, we could have an outcome where Z becomes bound to Y, and X is its bond with Y is broken. As Z is forming a new bond with Y, you could also imagine the bond between X and Y kind of dissolving and falling apart. Whenever this is happening, where you have bonds being made and bonds being broken, you go through this very high energy state, and it's actually an energy maximum. This is called a transition state. And transition states are represented on this coordinate diagram, which we'll draw in a second, as local maximum. And again, the transition states represent this point in time where bonds are being broken and being formed, but they're not completely broken or formed. So if we wanted to actually try to represent this graphically, we can utilize this reaction diagram, where reaction progress is on the x-axis, so start and stop of the reaction, and energy is on the y-axis. So very low on the y is low energy, more stable. Very high on the y-axis is very high energy, or very unstable. So we start out over here, x, y, and z, and we end where y and z are formed and x is broken. But to get from this x-y bond to this y-z bond, we have to go through a transition state. And so the reaction diagram would look something like this, where we go through a very high energy state and then we come back down. So notice for this specific example, the starting materials on the left and the products on the right have approximately the same position on the y-axis. So that indicates that this YZ and XY bond is approximately the same energy and approximately the same stability. So in terms of thermodynamics, what this would tell us, again, we're wondering about how much of thing B versus thing A. We could say then, in this case, because both of these have the same energy on the y-axis, they're both about as stable as the other. So given an infinite amount of time, we'd have about 50% on the left and 50% on the right. And this is not necessarily always the case. So this driver of how much product or how much reactant we're going to get actually depends on this end goal over here. Will this be really high or will this be really low? And depending on whether this is high or low is actually going to change the result.